Thank you very much for the introduction. So my name is Masaaki Kondo, the team leader of Next Generation High Performance Architecture Research Team of R-CCS. And today I'm going to briefly introduce the feasibility study project and current status of it. And we'd like to start with what the feasibility study project is. The feasibility study project is a national project promoted by MEXT, which is one of the ministry in the Japanese government, especially for technology or science or education or culture and sports. And this project started at August 2022. And there are three research topics. And one is system research, and this is especially for the proposed system image for the next generation supercomputer system, including architecture, system software, and application aspect. And the other one is the other one, two is new computing paradigm research and operation technology research. For new computing paradigm research, especially this studies hybrid of quantum and HPC computing. And for operation technology research, it examined items and metrics to be considered regarding the operation technologies and propose their goals for future system operations. And these research are separately called for proposal. And the 4 teams actually selected for this feasibility study project in August 2022. And we are one of them. We are doing the system research for next supercomputer system. And today's my talk is focusing on this one of the system research for this feasibility study project. And this is a very brief overview of our feasibility study project. I'm sorry for the busy slide. But as a successor of Fugaku supercomputer system, our concept for next generation system is still the system that is capable for very versatile computing, including, of course, the traditional simulation and also the AI, especially for AI for science. Therefore, we would like to have a generic capability in the next generation system with applicable for a wider range of applications with high effective performance. And so that we need to practice the flops to byte concept, which is we seek for the way to improve the data movement efficiency, because most of the HPC workload is memory bound or I/O bound. Therefore, that is very important aspect for this study. And we define 3 research groups. One is architecture research, and the other one is research on system software and library. And then we have a specific group for application research. For architecture research team, they are investigating the technological possibilities for future HPC systems, including 3D stacking, memory technology, accelerators, or chip-to-chip direct optical links, etc. And also studying the performance of entire system or each component of based on the trend in technological trend, based on semiconductor technological trend. And for system software, library research team is drawing specifically roadmap for future system software development in Japan based on, for example, inquiry to users. What is the specific software tools are necessary in the future? And finally, for application research group is to studying the next generation target science, and also create the benchmarking suite to evaluate the architecture candidate. And I would like to briefly introduce the activity and current status of each these research groups. From the next slide. Sorry, this is an organization chart of our research team. So there are a lot of researchers to collaborate with us. Especially for architectural research, we are collaborating with many HPC vendors, including Fujitsu, Intel, AMD, NVIDIA, HPE, and ARM. And also for system software and application research groups, we are collaborating many domestic researchers from universities and also national laboratories. So this is very big research group. And this is expected timeline for Fugaku Next or post-Fugaku system development. So we will follow the history of Fugaku development. Actually, it takes a long time, maybe 10 years of cadence. Therefore, if we follow the Fugaku history, it also maybe take 10 years of range. So we are here now. We are doing feasibility study, and we will have a development project in fiscal year of 2025. And we expect the next system will be deployed in around 2030. But we like to print the schedule if possible. So then I'd like to briefly talk about what we are doing in the architectural research. So here is a key concept in terms of node architecture in the future supercomputer system. This is actually our Solomon architecture or concept of next compute node. So this is an CPU part. This is an accelerator part. So we like to use some accelerator for energy efficiency in the future system. And then, because as I said, data movement efficiency is very important in the future. Therefore, if possible, we would like to have 3D stacking memory technology. I mean, 3D stacking memories on top of processing elements. So, and then we can achieve significant increase in relative memory bandwidth by 3D stacking memories. And also, if technologically possible, we would like to use silicon photonics to ensure high bandwidth for remote memory accesses. And this is our concept in the future generation architecture in the architecture. And as I said, one key research item is what kind of accelerator architecture should be used. And of course, we need a power-efficient compute node. Therefore, we need to explore the architecture for accelerators. And especially our workload is, of course, one important workload is HPC workload, traditional simulation workload. And also in the future, AI should be combined with HPC. Therefore, AI workload is also very important to be considered. Therefore, we would like to have truly useful accelerators for both HPC and AI workloads. And especially, most of the HPC application is memory bound. And for AI workloads, it's sometimes compute bound, but of course, it's a mix of compute and memory bound regions. And this figure shows roofline analysis based on S64FX execution of several HPC workloads. And we see that this is roofline curve of S64FX. So most of the HPC workload are around here. That means most of these benchmarks are, I'm sorry, the x-axis shows arithmetic intensity, and y-axis shows performance or in terms of flops. And so these applications can be memory bound applications. Therefore, for HPC workload, as I said, memory bandwidth improvement or relative memory bandwidth improvement is very important. And some applications like matrix multiplication is, of course, compute intensive. And as I said, AI workload can be categorized, part of AI workload can be categorized here. Therefore, for memory bound applications, maybe throughput optimized CPU or GPU is suitable. And for AI workloads, maybe matrix types of engine, matrix engine will be suitable. Therefore, we like to explore the mix of these processing components. Therefore, we are now studying or discussing what and how to integrate these compute components in the system. And also, we need to consider to improve effective memory bandwidth and to optimize data movement with high programming productivity. And then current candidate architecture is GPU or GPU-like accelerators coupled with matrix engines. And those should be connected to CPU. And this is candidate packaging technologies, because as we see end of Moore's law, the packaging technologies is very important for to consider future computer system. So of course, currently for chip-to-chip connections, sometimes we use monolithic die-based integration. And currently, many vendors are using this chiplet-based integration. And in the future, more aggressive chiplet-based integration will be possible. And if we have this kind of aggressive chip-to-chip connection, maybe we can improve the energy efficiency. And of course, it will be there are some technical difficulty or because these are aggressive technologies. And for 3D stacking technologies, currently we are using 2.5D connections, including connection between CPU or accelerated HP or memory. But in the future, maybe we can use 3D stacking memory on top of processing elements. Currently, some are possible. For example, hybrid bonding is possible. Therefore, for example, case of AMD CPU, the 3D cache is stacked on top of CPU. In the future, we look forward truly 3D stacking implementation. Many 3D stacking memory are stacked on top of CPU or accelerators. And this is, of course, very technically challenging implementation. But if this is possible, we can improve much more power efficiency or energy efficiency. And finally, for silicon photonics or co-packaged optics connection, it will be very desirable for high memory bandwidth between compute node and also power reduction of communication between nodes. And okay, so this is performance projection in future supercomputer system. And this is based on the estimated energy per operation on current and future technologies. Based on historical trend obtained by publicly available data. Therefore, this does not reflect any partner vendor's perspective. And we consider this performance projection based on the power budget limitation, like 30 megawatt power budget. And if under the assumption of 10 megawatt is dedicated for memory part, and 20 megawatt dedicated for compute part. And for simplicity, the network power consumption is omitted in this analysis. But of course, that's very important. And also, this analysis may not be realistic due to the other constraints, such as cost or thermal issue. But this is maybe good. This will be a good indicator to project the future system image. And for this chart, we show the aggregated memory bandwidth or system-wide memory bandwidth versus power consumption for several memory technologies like LPDDR or HBM or 3D stacking memory on top of processing elements. And the difference of these memory technology is especially energy consumption per access, especially for LPDDR. It is expected that the power consumption or energy consumption per bit is 50 picojoule or 20 picojoule to 50 picojoule. In case for HBM, it can be dramatically reduced to 2 picojoule to 5 picojoule. And if we can use 3D stacking memory technologies, it can be further reduced to sub-picojoules. Therefore, as we see from this chart, if 3D stacking memory technology is available under the case of this power budget assumption, we can achieve, for example, for LPDDR, only achieves 100 petabyte per sec in system-wide. By HBM, it can achieve 300 to 700 petabyte per sec, which is maybe several times larger memory bandwidth compared to Fugaku. And finally, if we can utilize 3D stacking memory technologies, it can achieve more than 1,000 petabyte per sec. Of course, this is very desirable memory bandwidth performance. And the same analysis can be done for compute part. And comparing traditional CPU-based system and GPU-based system, and also the matrix engines. Case for CPU-based system, energy consumption per operation can be like 20 to 50 picojoule. In case for GPU, it can be reduced to 2 to 5 picojoule per operation. And if we can use a matrix engine, it can be sub-picojoules, like 0.2 to 0.5 picojoule per operation. Therefore, of course, if we use matrix engines, it's very power or energy efficient. And therefore, under this assumption of power budget, if we can use matrix engines, free utilize matrix engines, we can achieve maybe over 100 exaflops for FP16, floating point arithmetic. In case for GPU, can achieve 2 to 4 exaflops. And if you use a CPU-based system, it may be around 1 exaflop in system-wide. So this is our current performance projection under the scenario of power constraint. Okay, now I'd like to give a brief introduction of system software and library research group activities. The objective of this group is to investigate technological trend of system software and draw a R&D roadmap based on it. So we are doing investigating system software trend, of course, and based on the trend, we are collecting the information to decide software development strategies in Japan. And also, we are comparing similar softwares and to select the best software and classification or to clarify alternative softwares. For the range of software, system softwares, we are studying a bunch of wide variety of system softwares, including scheduler, runtime, or I/O or file system, or OS virtualization environment, or, for example, communication library, compiler programming framework, numerical library, and AI frameworks. Among them, today I'd like to focus on the compilers and programming models and also I/O storage. So this is status of study of compilers and programming models. So we are, of course, considering the feedback from Fugaku compiler and programming tool development. One of the issues of Fugaku compiler and programming tool development is new compatibility or easy to use of compiler and tool chains. And then we inquiry to the application people, application developers about what kind of, for example, what kind of programming language are you using now, or what kind of programming language are you going to use in the future, especially if we use an accelerated kind of architecture, and so on and so forth. Currently, so most of a majority of users are still using Fortran, and then followed by Python, C, and C++. And some are hybrid of Python with Fortran or C or C++. So therefore, we know that Fortran support remains important. For accelerated programming, so more than half had no or little programming experience with accelerators. Therefore, we need support for porting and tuning effort. That is very important for accelerators. And also for performance portable programming, only a few have used it, but we know many would like to use it in the future. Therefore, also porting support or tuning support with SQL or HIP or C++ compatible programming framework is important. And this is status of storage and file system. Because of time, I summarized this slide. So especially we studied for DEOS file system as a candidate file system for Fugaku next. DEOS was developed as an open source software file system for the storage of Aurora in ANL. And we evaluated the DEOS in ARM environment, especially A64FX CPU environment. And here's the result of the evaluation, our I/O throughput. We varied the number of tasks, and we evaluate the bandwidth, I/O bandwidth. And we know that the DEOS is very scalable because it can achieve almost peak performance even in very short chunk of data access. So this is kind of our current status of file storage and file system analysis. In case for application group, so objective of application research is to survey computational resource requirement and also studying future target science. And also application people help us to create the benchmark of future, reflecting future computational science. And the details of the application research group effort will be given by next talk by Iwashita-san. Therefore, I'm going to skip this. And this is in summary and the current status of feasibility study. So we are, of course, taking care of application-first system design. So we'd like to design a system targeted for science breakthrough, not just for ranking, such as top 500. And by science roadmap, it is said that they need 5 to 200x effective performance improvement for 2030s compared to Fugaku system now. And therefore, for that purpose, we are doing the architecture research and consider the effective system architecture based on the analysis of benchmarks. And also for software, we are very conscious of a software ecosystem, and also we are now creating the development roadmap of system softwares. And of course, we need to collaborate with operation technique and new computing paradigm teams, for example, hybrid of quantum or HPC platform, or taking care of carbon neutrality, or etc. That's all about my talk. Thank you very much for your attention.